Move It really, it integrates state-of-the-art in motion planning and easy-to-consume package where as a user, all you have to do is give the configuration files and then you can use it. Good practices in software, the software development cycle, testing and code reviews and version control. And these are all things you can learn about on your own, but when you're actually doing it on a professional team, you're going to learn a lot faster.
For specifically those people where they do not have robotic companies around them, so what should they be doing and how should they be progressing in their robotics developer side? In robotics, electronics is one of the most important things, then software is an important thing, then theory is also important, and you create a good project after combining all of these three things. What do you suggest? Is software going to have more opportunities, hardware or theoretical side? So your title is robotics scientist. What's robotics scientist and what's robotics engineer? As being a maintainer, what is the experience required? How do you start it and how to progress and become a maintainer of something? Why we need admittance controller and how do you brought it to ROS2 control? What are the steps of it? Mostly people don't want to actually read documentation, and then I have to create a YouTube video for that. And then people look at, oh, this was the thing. And I said, I'm just repeating the things that are documented. But I think people now prefer video instead of reading, but that's what it is. If you want to hire someone, what should be his characteristics and what would be the ideal person if you hire someone? Today we have our very special robotics scientist as a guest named Paul Gesel. How are you, Paul? How it's going?
Yeah, I'm doing pretty well. How are you doing?
I'm good. So you currently work at Picnic and most of the people know what Picnic is doing. It's supporting Move It too. Tell us about Move It and how Picnic is evolving this manipulation side of robotics.
Yeah, so Move It is sort of the de facto standard for ROS if you want to control a robot manipulator. And Picnic is primarily supporting it. I'm a maintainer now on Move It. I've made several contributions, mainly small fixes and bug fixes. Maybe one of my bigger contributions to Move It was a new smoother plugin for servo. Helps the robot not accelerate too quickly when you send commands in different directions. But yeah, Move It really, it integrates state-of-the-art in motion planning and easy-to-consume package where as a user, all you have to do is give the configuration files and then you can use it. And these files consist of a URDF, which describes the kinematic structure of your robot, and then different YAML files to say your acceleration limits and trait limits and maybe sensor configurations.
That's great. So I was looking at your profile. You started bachelor's, master's, then PhD, and throughout this whole period, you worked for a small amount of time in MathWorks, then internship at Picnic. So as you were researching in your PhD, you went into MathWorks as well. So what were you doing there and what software you were working on and how does it went?
Yeah, so at MathWorks, I was working on their ROS toolbox. So MATLAB has a ROS toolbox, which is designed to essentially everything you can do with the standard like ROS with C++ and Python. They support custom message generation. They have publishers, subscribers, and services. They support ROS1. They support ROS2. It's funny because I feel like I was able to get ROS working on Windows, using MathWorks toolbox before I was able to get it working with the official, this was quite a while ago. But yeah, inside of this project, I was specifically working on mainly Simulink. So they also have support to do ROS topics over Simulink, which is, designed to be deployed onto actual hardware. And specifically, I made some features to read and write point cloud data and image data and laser scan data. And then towards the end of the internship, I did a little bit of work on the core MATLAB product in processing camera info messages. But it was a really good experience because it was my first software internship, which meant I got to learn about, good practices in software, the software development cycle, testing and code reviews and version control. And, these are all things you can learn about on your own, but when you're actually doing it on a professional team, you're going to learn a lot faster. I think it was a really good opportunity for me.
So you were sort of adding features into actual MATLAB core, the main software of it. And what's the language they usually prefer?
So in this case, I was mainly working on Simulink, and these blocks, they call them, you can write them inside of MATLAB. So I was mainly doing all of the coding using MATLAB's actual language.
Okay. So I mostly get this notion that doing things in MATLAB is good for research, but when it gets practical, bringing that code and writing the interface for MATLAB and to the actual hardware is very hard. Is that true or is that just a myth?
They've done a lot of work to try to make it easier to like deploy MATLAB code on an actual embedded system, for example. So MATLAB has this toolbox called Coder, which will take MATLAB code and generate C++ code. You can generate GPU CUDA code as well, but you can like prototype something and then generate this code and try to run it on a Linux system or something. They have like tooling to sort of try to deploy the code. But a lot of times, and in robotics, like people are using MATLAB in academia to prototype their concepts and just as a helpful tool.
So you went into MATLAB after doing the masters. Most of the cases, what happens is people start in undergraduate basic Arduino-based robots, ESP32, Raspberry Pis. They perform line following in small projects like these. So what do you suggest for the people? How should they be progressing? Just an advice, obviously, it's a very general question in mobile robotics specifically. For specifically those people where they do not have robotic companies around them. So what should they be doing and how should they be progressing in their robotics developer side?
And did you say specifically for mobile or just in general robotics?
Mobile robotics, because mostly people start with mobile robots.
Yeah, I was going to actually say that I think it might be worth it to look into simulation because the thing is that there's a bunch of concepts you're going to learn if you work with a robot manipulator that just won't exactly be applicable to a mobile robot. You're going to have to deal with forward kinematics algorithms, inverse kinematics, and as you go higher and higher dimensional and you have more and more joints, algorithms like A-star stop working as well, and sampling-based algorithms like RT become more and more valuable. So there's a bunch of fundamental robotics knowledge that you're going to get working with a manipulator. And that's why I mentioned simulation, because you can run simulation for free. So I've had a lot of good experience running MuJoCo, and they have like Python bindings. You can load a URDF file, and then you can play with this. I guess you can also use PyBullet. I haven't used it before, but I've seen a lot of people do this. And because like once you're using this robot manipulator, you've sort of gone from 2 dimensions to 3 dimensions, and there's a lot more factors to consider, especially if you're talking about vision and you want to do like estimation of an object, estimating the X, Y, Z position and roll, pitch, yaw. There's 6 sort of degrees of freedom to this rigid body, as opposed to in 2D. Yeah, it's a much simpler problem. In the case you explained, it's like they've already showed competency with hardware, these low-level skills, like connecting the motors to the Arduino and such. So I don't think that would be anything against them that they're doing the next project in simulation.
Because things get very sort of vague as well as what should we focus on in robotics. Electronics is one of the most important things, then software is an important thing, then theory is also important. And you create a good project after combining all of these 3 things. So it becomes very confusing after a certain level, what should we progress into? What do you suggest as you were in the field of it? For the future specifically, is software going to have more opportunities, hardware or theoretical side?
Yeah, to me, I feel like there's more to do on the software side. Like in robotics, you have sort of the mechanical engineers designing the motors and the actual mechanical structure, and you have electrical engineers doing the electronics. But there's still like lots of advancement, to be made on the software side on how do you actually control this thing and how do you connect perception to control. And like I said, these things can be done in simulation 100%, right? The same algorithms are going to run there as they're going to run on the real robot. And there's some sim to real gap. So maybe it's not going to work perfectly, but you get to really implement state-of-the-art methods. Whereas if you're trying to build some electronic components yourself, it's just too much to ask for one person.
Definitely. So the main person to get into robotics hardware side should be very specific to their degrees: electronics, electrical engineers, gearboxes, and the design of the robot, mechanical engineers. So it becomes a little bit confusing, but we will explore later in the discussion. So your title is robotics scientist. I think I got it for the first time. What's robotics scientist and what's robotics engineer?
Right. So I would say the main difference between the scientist or the researcher and the engineer is that the engineer is probably going to be solving some task with like a specification, right? So it's like, we have this robot and we need to get it to move from point A to point B. We have this kind of hardware. So they'll go and say, all right, let's look at the list of libraries we have available to run the planner. How are we going to integrate that into our stack? How are we going to make it maintainable and minimize the amount of effort we have to put to get this thing working? And how are we going to maximize reliability? The engineer is focused on really practical problems that are specifically problems that the company or business has. Whereas the researcher is like looking, one step beyond that, maybe a bit more towards the future. But you're solving these higher risk problems where you don't know if a solution exists or not. Like that's the point of doing your research. You're trying to discover information. You might say, oh, can we actually use this new kind of model to control a robot? No one's ever done this before. So that's my hypothesis. If we get some data and we train this model, we're going to be able to get the robot to do food preparation. So you try this, maybe it will succeed, maybe it won't. But it's the job of the researcher to discover that information. And like once this is known, now the engineers can take this knowledge, they can reinforce it, right, and integrate it in like a fully fleshed out way into the stack.
Interesting. So after doing the masters, you went into MATLAB and performed some software side of things, software development. Then got back into your PhD side and did some research. So a developer experience and a research experience. How did the developer affected the research side of it? Because it's totally different thinking sides.
I think it affected it in a positive way. Like I said, you really learn to use these technologies like version control, right, in a proper way. And like when you bring that to your research, it's just going to help you. When you're starting out in your lab, there's so many problems to solve. Like it's hard to go to your advisor and say, I need a week to learn Git. I need a week to learn this like technology. It's like they want results. It's like you're sort of supposed to know these things. But so if you have 10 weeks to go and do this internship, you're going to learn all of these different things, and then you can take it back and apply it to your lab. Yeah, and it's going to help out. For example, when I finished my internship at Picnic, I went back to my lab, and the first thing I did, I went, hey, let's try to use Docker for these like robot deployments that we're talking about, because we had all the drivers and they're sort of installed on this robot, but we were going to get 10 more robots, and it's like, hey, we should really look into this. And I think it helped out the lab. So yeah, taking these learnings back is very beneficial. And some of the bigger labs, they'll have like a lab engineer there. And it's like this person's responsibility to do this maintenance, to help out the students, and to maintain these kind of things. But in a smaller lab, like the lab I was from, that's all on you.
I think this is very essential. Even if you are a researcher, because all of you are working around the code. So these development tools, the dev operations should be compulsory, I think, to also not just for your own learning, but also to help the colleagues around you as well, because code sharing and making things work, it becomes very easy if you understand these in deeper detail. So you had an internship at Picnic, you had an internship at MathWorks as well. So what's your experience? Because the nature of the customers for both of these companies are different. So what was your experience and the software base that you worked with? How much different it was?
I think it's quite a bit different. I mean, for one, with MathWorks, like all of the stuff you're doing, it's all going to be proprietary, right? And behind the software that they sell. Whereas Picnic, there's a lot of open source work you do. Your name is going to get on these packages that other people are going to use for free. And another huge difference is just the size and scale of the company. So, in MathWorks, I was on the ROS Toolbox team, right? So there's a whole team of people dedicated to getting ROS communications to work and, ROS message parsing and such. So you get to take your focus and really narrow it and become highly specialized and like solve the problem really, really well. Whereas at Picnic, in comparison, it's a much smaller company. So what winds up happening is that you have to wear a lot of different hats, right? You have a lot more responsibilities and you need a wider base of knowledge. And then there's like the community aspect to working in open source, right? So you would go to like developer meetings, for example, for Move It. So you kind of get your name out there a little bit. So definitely a few differences.
So at Picnic, it was more on the developer side of software, and it was open source. With open source, you have sort of less responsibility, but you have to think a lot for the reason that it is going to be used by a lot of people, and we know Picnic supports Move It, and Move It is utilized a lot. So as being a maintainer, what is the experience required? How do you start it, and how to progress and become a maintainer of something?
Yeah, like a lot of these ROS projects, the bigger projects, they actually have maintainer meetings. So ROS Control, they have maintainer meetings every 2 weeks. Move It has a maintainer meeting once a month. So I would start going to these meetings, and they're open. You can I think you can find on ROS Discourse probably the schedule for these things. But you can just join the meeting and ask them questions and ask, oh, what can I do? Are there any problems? And there are like issues that are marked good first issues sometimes. But even if they're not, if you go to these meetings and you're showing you're willing to work and you want to learn, I think people will, be willing to communicate with you. And try to give you a good project to work on. So you can just join these, you can ask for work. And then as far as like becoming a maintainer, in Move It, for example, what it is you'll make a few contributions, and I don't remember the exact number, but after making a certain number, the group sort of votes whether or not to add you as a maintainer. So there's a system, and as long as you've made it, all the requirements, then you'll be added officially.
So before contributing to it, obviously you need to understand the code. With your current experience, what do you think, how much knowledge one knows? Because you might need to understand Move It as well, and then ROS too as well. Is that the requirement? What level of structures that ROS2 and Move It have? How in depth you need to understand them before contributing?
Yeah, Move It is a bit of a complex project for a beginner to get into. I think you do need to know ROS, right? There's sort of publishers and subscribers and services all over the place. There's like quite a few plugins, so you should try to know how the plugin architecture work, and they use like plugin lib. And then the code itself is also like highly technical, right? So in Move It, just a brief summary, there's this concept of a motion planning pipeline. And basically what happens is, you have all your configuration, your URDF, your YAMLs, and that creates this thing called a robot model. And the model just describes like, how does the robot move? Where is it allowed to be, right? There's collisions in the world and such. And the point is using this model, you go through a few processes to generate an actual trajectory. One, you do a motion plan to find just a collision-free path from wherever the robot currently is to where the robot wants to be. And that's just a path. It has no timing information at all. So then there's a second stage where it does time parameterization. And the default algorithm is something called TOTG, time optimal trajectory generation. So it takes the path, turns it into a trajectory. And then finally, the last stage is something called a trajectory execution manager, where it takes this trajectory and it feeds it to ROS2 control. And you can do it without ROS control as well. But yeah, that's a general pipeline. So everything in Move It is sort of built around that concept of loading your robot in, doing motion planning, generate trajectories, doing post-processing on these trajectories, and then finally sending it out.
That's a lot of information, by the way, in 2 to 3 sentences. So it's path through trajectory, then finding the time and optimizing that while collision avoidance.
Right. And the collision avoidance comes from the sampling based algorithm, right? It generates the collision free path. And the thing is about Move It is, in general, it's sort of planning for a static scene, right? So if you have a collision free path, regardless of how you parameterize this thing with time, there's never going to be a collision. And I think there's some checks where if you've planned and you start executing and then the scene does change, like it will stop the execution because maybe there's a collision now because something moved, right? So in that case, you'd have to plan again. And then there's even some hybrid planning, which is designed to sort of have a hierarchy of planning. But yeah, that's even more complicated. One thing I like to do to get familiar with a code base that I don't know, one, pull all the code down, build it from source, right? So, I mean, of course you can install this as binaries and you can run this, but if you run into some issue, it's like, you're going to have to look at the code on, GitHub and try to find out what's going on. So pull it all down, build it from source, and I build it in debug. And then what you can do is you can run the application and you can put a breakpoint somewhere deep in the call stack. Like you find out where the motion planning actually happens, put a breakpoint there, and then your application is going to get here and it will stop. And then you get to see sort of the whole stack frame. Like, how do the abstractions work? At the highest level, oh, we see a ROS node and it's spinning. Okay, great, right? That means it's like waiting for some motion planning request. And then you go down a bit lower and you see, okay, this is where the callback for the motion planning request happens. And at this layer, I can see it did a pre-processing step. It's now doing planning. The next line of code says post-processing, or do time parameterization. And, step down the stack frame a little bit more. And you see, this is where it actually connects to OMPL. Like in your IDE, whenever you click on these different frames, it jumps you right to the file, right? So all of the relevant files are sort of automatically going to pop up. So you got to find, one question is like, well, where do you put this breakpoint? So that requires a little bit of knowledge because you're like, okay, I know OMPL is used, so let me find out where OMPL is, put the breakpoint there. Another thing you could do though is like if there's printing that happens, you can search the code base for that line of text and put your breakpoint there. And then at least you'll be able to stop the application at this point, which is a critical point because it's printed something like solution found.
That's amazing strategy, by the way. But for the people who don't get scared by looking at the code, because a lot of inheritance polymorphism is visible, but that's really great that you have mentioned that. Get the code, put the breakpoints where you are interested and want to find how things are working. Amazing. So have you maintained any ROS-based system, ROS package, or just Move It side?
Yeah, I've done some other contributions, and then I do maintain one main package basically. So during my internship, I mean, I think I worked on the admittance controller, and as part of the process here, we were dealing with ROS parameters, and no one really had a great solution at this point because the way parameters are done is inside of the C++ code, you're going to define the name of the parameter, and you're going to say, oh, get this parameter if it exists. It's just a bit hard to keep track of because one file might declare a parameter in another file, and there was no standard way of doing this. So as sort of a side project during the internship, I implemented this package called Generate Parameter Library, which
I was about to
essentially
ask
what it...
about that.
Yeah. So that's the package that I'm the sort of creator of and primary maintainer still.
First, finish the part of why we need admittance controller and how do you brought it to ROS2 control. What are the steps of it?
So let's talk about the admittance controller. So one thing, for those who don't know, admittance control enables you to do force-based control of a robot which only supports position-based commands or velocity-based commands, so long as you have a force torque sensor. So many robots, they don't have any sort of access to actually send joint level torques directly. And this is a problem if you want to do torque-based control. Like sort of controlling the torque as a function of position. This is like impedance control. And like I said, this kind of control, it's not easy to do, right? If your robot doesn't support it, you're not going to be able to do this. Where admittance control sort of flips it around. And it says, if you have a force torque sensor, what you can do is you can sense the force. And if the force is higher than expected, you can back the robot up away from the object that you're touching. Or if it's too low, you can sort of push the robot into it. So it's actually changing the position of the robot as a function of the force, right? It's like for inverting what the impedance control is doing. So it's a very useful controller because then you can do force-based control on these sort of industrial manipulators. And yeah, during my internship, that was basically what I was tasked with. I showed up and there was an existing prototype for the admittance controller, and I was asked to get that, finished and merged into ROS2 control. Yeah.
That's great. So what is the process of getting your custom controller into ROS2 system?
They do have a whole plugin system. So if you want, you can develop it in your own repository, in your own repo, and then you can just have that loaded in. So there's no problem if you need a proprietary controller or if you just don't want to go through all the effort of merging it into the official ROS control. That can easily be supported. But if you want to actually merge it into ROS control, there's a few things I would do. One, I would show up to the maintainer meeting and just tell them, you're interested in this, how to do this controller and you want to get it merged in. Because the worst thing that can happen is that you do all of this work, you make 10,000 line change and you make this awesome controller, but then they go, oh, we can't use that. This is some cool reinforcement learning controller you made, but it doesn't work with our stack. Sorry. Because now you just sort of got burned. You could still use it because of the plugin system. But yeah, so I would go there, I would tell them what your intentions are, sort of get permission, and then they'll help you too. Right? Every 2 weeks, you can come back and say, I ran into this issue. And they'll actually, spend some time answering your questions. They do have an agenda, though, so they'll get through all the other points first. So one, get permission. And you could use a GitHub issue, too. You don't have to go to the meeting. Tell the maintainers that you plan on doing this. And once they give you the go-ahead, now start coding it. And then in general, you want to make sort of smaller PRs. It's to do with a controller, though. Because, what are you going to do? Make a PR that, has a half-working controller? So yeah, I didn't really follow that piece of advice when I did the admittance controller because it was a giant PR. But yeah, essentially what you're going to do is get the permission, start implementing it, and you should be able to get it merged in then.
You should be able.
It is going to be
Sure.
It is going to be a long process. That's it's very likely to take 6 months to go through this whole thing.
Yes, and the level of knowledge required is very good C++, because even if you look at the plugin thing and you want to plug in your code, you need to go through this the structure of the plugin, that how it is created and how time is controlled and which function to call. Although I have not yet created any ROS2 controller plugin, I have been working on the path planning side. We recently created a path plugin and it was a little bit difficult. So for people who are listening, things are very easy, but there is some sort of complex C++ software that you have to look at as well. So Paul, as you are mentioning about the thing that you have done, admittance controller, that only requires a robot and a force torque controller and the backend. Interesting thing is you are doing two things in what I can see. You are going through a lot of theory. You are looking at a lot of mathematics side and force torque physics comes in. You are also looking at the software side. You are at a level of understanding how ROS2 controllers work, how ROS2 works, obviously, but in under the hood, how ROS2 controllers are working and how I can integrate my plugin into it. There are a lot of things inside of it before getting your code to the whole open source system. What do you want to suggest to people who are just looking at things in the perspective that ROS2 is just about nodes, services, and launch files?
Yeah. I feel like it's a bit of a complex situation. One thing is, I actually saw one of your videos where you explained, like, oh, when you create a ROS project with, the ROS package create, here's what we'll create, and here's all the different files. And you're explaining, like, the sort of, it's really complex, and, like, what do all these things do? But I think that's extremely valuable, actually. I think you need to, like, it's very easy to say, okay, this thing works. I'm going to copy and paste this thing in. I'm not really sure what it does. But all these things do have a purpose. And when you understand the purpose, it's going to help you understand the whole, the whole configuration, the whole process. And for like a ROS control, for example, it is a bit confusing, but like when you actually, if you make a contribution to it, you're going to see, oh, this is where this plugin loads and etc. And then it's going to like make sense. For example, I think one thing that probably confuses a lot of people with ROS control is that the hardware interface, it's a plugin, and that's loaded via the URDF file. So inside of the URDF, there's a ROS control tag, and it says which hardware plugin to load. But the problem is the URDF file is installed on the system, probably. Like, so you can search your entire code base. Oh, do I have access to this hardware? And you're not even going to see it because it was actually included via a Zacro. And maybe it was like in a Zacro and a Zacro. So there's like so much sort of separation between you and the actual plugin that it feels like magic. It just somehow works. But like just knowing that, like, okay, all the plugins that are loaded, they're going to be loaded based on the URDF. And they're all going to be loaded sort of sequentially, right? Immediately read and write is going to start getting called. Then, you're going to load a controller, and the controller's update function is going to get called. I think sort of having the architectural understanding of ROS control, which there is actually documentation for it. I wrote some of it during my internship. I think it's extremely helpful.
It is helpful, but I'm on the education side of robotics, and I sometimes do development in some projects that I get. But you know what happens? I get the request of what does this parameter means. I send them the documentation, but still they don't understand. Mostly people don't want to actually read documentation, and then I have to create a YouTube video for that. And then people look at, oh, this was the thing. And I said, I'm just repeating the things that are documented. But I think people now prefer video instead of reading, but that's what it is. So coming back to your direction in manipulation side, so what currently are you working on, computer vision side or motion planning? Because these are the two important things that I see in manipulation, or what you are currently working on.
So yeah, I mean, at Picnic, I've done quite a bit of different things since I've been here. I'd say the last two big projects, one is in simulation actually. So we did quite a bit of evaluation and integration of different simulators, and we decided to take the MuJoCo simulator and sort of make this our new default, basically. So there was a lot of work to be done there because we've hooked it up to ROS control, for example, turned it into a hardware interface. So there's a lot of learning as well. Like robotic simulation is its own area of study. I mean, I know you said the documentation, people would prefer videos, but there is good documentation on the MuJoCo as well. So one thing was sort of doing simulation, right? A lot of work there. Number two, I've been looking into lately running different machine learning models. And we've been looking into the ONNX format, which is designed to be, ONNX is a open neural network exchange. It's a sort of cross-language format, like description of different neural net models. In looking into this, like trying to pull in these state-of-the-art models to be run in our stack.
So as you are working as well and looking into AI side of it, deep learning side of it, so how do you study about this? As for a person who knows about robotics, who knows about manipulation, mobile robots, drones, something, but robotics side only. So you're looking toward vision side of robotics. So how do you study about this? Do you go from the very scratch, ML, DL, and then generative AI? How do you are approaching the steps of learning it?
And just to be clear, we're talking more about finding somebody's state-of-the-art approach, trying to understand it, incorporate it, not making your own and then training your own model or something. Okay. Yeah, because that's like a much, much more complex problem. Even finding something that's out there though that's going to work for you and that maybe you can adapt, it's still a bit tricky. And I think I can talk to that at least. So one thing is, I mean, if you're on like LinkedIn or Twitter, you can follow these like researchers, like these famous researchers from these different institutions, and they'll go and post their results. And these things will actually go, you know, a little bit viral if it's a really impressive result. So like sometimes these things, they'll just actually come right across to you, like in your feed if you go and you intentionally follow the right people on these social media platforms. Even on GitHub, by the way, you can follow people. And every once in a while, I'll see like, oh, that's interesting. Somebody started this new repository, and I look at it and say, oh, wow, this is like a, you know, it's a new version of segment anything, but it has less parameters. It's designed to be run on an actual like embedded system or something. So like, you should take advantage of these like algorithms, right, to find this information. That's one. Number two, like if you find some paper that's impressive, like maybe they're doing point cloud processing, like you can take the name of the paper, put it into Google Scholar, and then you can hit cited papers, and you'll see, okay, everyone who cited this paper, which means it has to be newer. And if they're citing it, it's probably because they're at least doing a similar work in the same domain. They might directly be comparing against it. So you go through this list, find a bunch of free papers on archive, you click on this thing and say, oh, wow, here's like a new paper that beat that one from 2024. And the first thing I do when I open up the paper is Control F for HTTP and see if I can find a GitHub link. And if I do, then I say, great.
A pure software developer approach. But I think that is necessary. I don't understand why, but why would I read your paper if I can't run your work and I cannot see it in action? I don't know. I think researchers do that thing, just read it. But if there is no code, how can they verify that this work is authentic?
There's like multiple things going on there. One, like, you know, in the past, it was just less common to do this. So as time goes on, I think more and more people are doing that. Number two, like you would be surprised, but if you email the researchers, like they'll put their emails in the papers and you start asking questions, they will respond, and they might even send you the code, even if it's not publicly available. And, you know, the reason the code's not there is it's just more work. It's not actually required. And, you know, the code's like very messy. There's like 20 dependencies you need to install on an old version of Ubuntu, right? So it's just like they've moved on to the next thing already.
So talking about some algorithmic side, you said for motion planning, there is sampling based approach. What are the other approaches for manipulations? I also want your perspective on 3D planning for drones or manipulations. So what are different approaches of planning and how we look at these things?
Yeah, I think planning is like a very big domain. So on one case, you could have sort of optimal planners. So this is something like A star. If you come up with a heuristic, you'll find a solution faster. But ultimately, the purpose is to do search over a space and, you know, find a solution which is optimal with some cost function. So you can do shortest path. And that kind of algorithm works really well on like a 2D grid, for example. But these things are going to suffer from the curse of dimensionality, which means that as you go higher and higher dimensions, it's going to take exponentially more time and memory in order to compute the solutions. So certain domains that those kinds of algorithms work really well on. Then you have sampling-based algorithms. And these are interesting because they take advantage of dimensions of these problems are very large. So they can't be enumerated like with A star. So instead what you do is you sample the space and you just try to find paths through the space connecting these sampled points. And it just turns out like there's a property of these algorithms where they'll explore the space very quickly based on sampling randomly and connecting nearby nodes. So these kind of algorithms are going to be useful for something like a robot manipulator, where you're just doing planning in free space and the only obstacles are maybe like a table near you, or the robot itself is an obstacle. But they can actually struggle in certain cases, like if you have a very narrow passageway that the robot needs to move through. Like these sampling-based algorithms might not be able to find a solution because the odds of them sampling these exact points needed to get through are very low. Then there's sort of the reinforcement learning side of things. You can have the robot, inside of a simulation, you give it some cost function that says, okay, get from here to here, and it will just play over and over and over until it finally finds a solution. There's like real-time dynamic programming, which I think maybe you could consider like a reinforcement learning, but there's methods like model predicted path integral, which is an interesting idea. You can essentially simulate random actions, and some of them will do what you want, some of them will not do what you want, and then you can nudge the trajectory towards the sort of good trajectories, and you can do this over and over in a loop. There's like more classical control methods. You could use like LQR or iterative LQR to, generate a trajectory for the robot arm to go from a point to a point. The thing is, once you start doing methods like, trajectory optimization in MPC, they're very beneficial in that they're going to find solutions fast. They're going to be like time optimal solutions, but there's a certain chance they get stuck in a local minima. Like the problem, for example, where there's the slot you have to get through, like the robot's probably not going to be able to find a way through that path. But at the same time, these algorithms, you can put constraints on them. So if you have some sort of domain knowledge that says like, okay, over the trajectory, I know at some point the hand is going to have to be here because it has to go through the slot. You can add that as a constraint in your optimization to sort of, guide the solution through these tough spots. So there's sort of endless methods for doing planning, and control.
Move it, default way of planning is?
Yeah, so the default way of planning is to use a sampling-based motion planner. They're specifically using RRT Connect mainly, which is a variation of the RRT algorithm to generate a path in the C space of the robot. But the thing is, like this path, it has jagged edges, right? If you're doing straight lines through the space, there's these points with like 90-degree corners. So from there, you have to do some trajectory processing. You have to smooth it. You have to make it a continuous path, or else the robot couldn't execute it without constantly coming to a stop at all these sort of waypoints. So I don't know if that's in the TOTG algorithm or if it's another step, but that path has to be blended. They have a blending radius, which will merge the two like corners into each other with a smooth line. And then, like I said, you do the time optimal trajectory generation. And essentially how that algorithm works is that you're saying, given my limits on joint acceleration, generate a motion which will get to the end as fast as possible. And in the typical case, the velocity profile looks like a trapezoid. Like you're constantly accelerating until you get to your max speed. You then maintain that speed as long as you can. And then right before you're about to get to the end, you decrease the speed as fast as you can to wind up stopping.
A very short robotic arm technical workshop happened. Thank you. You are a robotic scientist. And if you want to hire someone, what should be his characteristics and what would be the ideal person if you hire someone? I understand that people should be good, humble, good at work, these general quantities. I'm just asking for technical things that person should be good at.
Mm-hmm. And you're asking more like a company like Picnic, for example.
Yes, definitely.
Right, yeah, because if it's something like NVIDIA, they're probably going to be really, really focused on their research record and the amount of citations and how big are you in the field and how influential and stuff. Where all these things matter, right? If you have these huge publications that you've moved the field in a positive direction, like that's great, but most people don't have that. So I think that's not a reasonable criteria for us to have. But yeah, what are some things I would look for? One, I look for like a strong theoretical background. So ideally, they're going to have at least a few papers published in top robotics conferences, right? I mean, that shows their technical rigor, their ability to do novel research and sort of come up with this solution. And, they do contribute to the field. So I think it's definitely a plus if you have some publications at these conferences like ICRA and IROS and RSS, Coral, just these top conferences. That's one. Number two, I think it's very important that you have some actual like hard skills in software engineering. So if your GitHub just has like nothing, or if it has like some projects with just one commit that says like upload code, like it's important that you actually develop these skills and try to make this thing look more like a professionally made like software project, basically. I think it's very easy as a researcher to sort of get stuck in like, you just make a prototype, you make a proof of concept, and then, that's it. You're done with it, right? You have sort of the 80% solution and you leave the rest of the 20% like, somebody else will figure that out. Just because you're a researcher, it's not an excuse not to know CMake or not to know CI and not to write tests. So yeah, I think if you can show strong research and software skills, you're in a pretty good position.
What would you think about a person above your level? What should be his technical understanding and level of sort of lead robotic scientist?
I don't know. I don't think I have a really good answer for that. I mean, previously we had Mark Moll at Picnic, So I guess I'm
Okay.
sort of thinking about him. And he was, he's a well-known researcher. I don't know if he founded OMPL or if he co-founded it, but he was a huge contributor to OMPL. He's done, all this contribution and planning and such. So yeah, I guess if I gave an answer, it would be like a senior academic. Like it would probably be somebody who made bigger contributions. Like they still don't have to be the top, but bigger contributions in the field of like motion planning. And then they decided, hey, I'm going to move from academia to industry, and they decided to come to Picnic.
That's great. That's great. So, do you have any plan of getting back to the research academic side, or going towards more on the software side?
I don't have any immediate plans. I feel like at the moment, anyways, I'm still learning new things every day. Improving my sort of software skills. I think there's still a lot to learn here, and there's a lot of benefit, like to me personally. And maybe like as time goes on, if I feel like I'm learning less and less and stagnating, at that point it would be time to, make a decision on changing something. But for now, yeah, I'm pretty satisfied here. There's still so much work to do and really research to do as well.
Interesting. So I was discussing yesterday with Francisco. He's also a professor, and there was one thing that I wanted to ask him, and I know the answer is not very simple, but the problem here is coming back to the part that ROS and MoveIt have big structures. You need to understand the software architecture. Then, as you suggested, get the code base, put the breakpoints, and run the code, and go through the code and find where things are calling each of these things. So it's like software architecture of robotics, but very few content is available. What do you suggest? How one should be learning software architecture and going through these big giant softwares and libraries like OMPL? We have Nav2 stack, we have ROS to control, and move it as it is. So what do you suggest how to approach this, and how to get to the level of understanding all of these?
Okay. Yeah, I think one thing is you need to at least have a base level of sort of programming skill on your own, for example. So if you're sort of just starting programming, I think you definitely need to focus on the fundamentals. Like it shouldn't be something that takes any cognitive effort to think about an if statement or a while statement or recursion. It should be pretty simple. So like those things are things that, and it just takes time, by the way. Like you need some repetitions. So one, get a base level of knowledge and sort of programming. Number two, I think it's definitely like asking too much, but if you like tried implementing these things on your own at some point, I think it would start making a lot more sense why they chose to do it the way that they did it. For example, theory, like, okay, there's going to be somehow generating a robot model, doing the motion planning pipeline, executing. Given just those things, you could start sort of prototyping like, okay, how would I do that, right? And as you get more and more experience in software, I think you're going to find like your guesses on like how would you do that, or how would you do it in sort of a ROS way, it's going to be sort of more and more accurate. And then you verify that assumption. So it's hard to say without any experience. Like I think as you get more experience though, you're better able to sort of guess, okay, it's going to be like this, and then verify your assumptions. I mean, I think it'd be pretty awesome if somebody made a video though, like who's very intimately familiar with Move It, and they did a series explaining the whole thing.
Okay, I've written this as a task, but I need to first understand with someone how things are working. I think I will ask a lot of questions to you, and then I will create a video for you. What do
Yeah,
you
I think
think
it'd be
about
really
this?
beneficial. I think it'd be really beneficial for people. And yeah, I can answer your questions.
Oh,
And we have more
that's
people.
great.
We have
Yeah.
other people at Picnic who are very, very experienced with movement.
Oh, that's great. I think it is very important because in general terms, what happens is you start using MoveIt, and what happens, you bring your URDF, you integrate controllers and move it, and everything is done. But there is very few content available how to get onto the real hardware. There is documentation, I understand, but getting to the real hardware, then selecting which controller is should be the choice for the problem that you are solving, how to configure and make changes inside of it. And regarding the part of adding your controller, I have not gone through any of the videos available online, but there should be, because MoveIt is a very powerful thing. Coming to the part of future, what is the problem that you want to solve, and what's coming next in the manipulation side?
I think there's still a lot of potential actually in more traditional methods where you're sort of more model based, and you're still using things like RT to do planning and trajectory optimization. And we see that in a few relatively recent papers released. There was Furobo from NVIDIA, where they're doing trajectory generation in real time using GPUs, actually, right? And their strategy is to do many plans in parallel and with different seeds, and eventually you wind up getting really high quality motions. So that's a paper. It's not really, it's sort of a new implementation of existing algorithms, but in a way that's now sort of unlocking this real-time motion planning, right? Which is very valuable. There's also a paper, their GitHub is called VAMP. It was by researchers who are at Rice University, I think Zach Kingston and William Thomas. But what they did is they formulated the motion planning problem in a very, very structured way where they could utilize sphere-based collision checking for the robot, and they could utilize SIMD instructions to do accelerated motion planning. And they showed they were able to do like motion planning solutions much, much faster than MoveIt. And MoveIt is already pretty fast, right? So there's still advancements being made there. I think there's still like a lot to be done. And then, on the model-based side, there's the whole side of task and motion planning. So there, you'll describe your world sort of symbolically. You could use PDDL, for example, that says what are, all the things in the world that the robot can interact with. And you combine motion planning with task planning in order to get the robot to do long horizon planning in sort of an optimal way. So I think there's still lots of work to be done there. And then on the other side of it, we have sort of the deep learning end-to-end based control methods. And these methods have obviously had very impressive results, and I don't see an obvious limit on where they're going to stop, right? So as long as you give more and more data for like the specific task you're doing, they wind up doing really well, and they can do complex manipulation tasks like food preparation. So both areas are, I think, really exciting. And I would say there's probably more to learn, sort of more to discover on the deep learning sort of data-driven control side of things. So if I were to pick one of these directions, I would put some effort there.
The classic available approaches are already really good, and data-driven decisions and model-based systems should be the next research domain that you recommend.
Yeah, I think that's right. I think there's still, there's lots of things to learn. And I guess maybe the only limitation there is like, as these things scale, like it starts getting unreasonable, like inaccessible for anyone to access this, right? Because they have these massive GPUs to train these models. But I think there's still a lot to do, even if you don't train these foundational models, right? You can train individual skills, for example, and then maybe you could use more of a hybrid approach where you have classical methods doing the point-to-point motion, but when you have to do something complex like plug in a plug or spread sauce on a pizza, switches over to the learn method. Because these methods, they can be trained on a desktop GPU. You don't need this extremely expensive equipment, actually.
Definitely. But in most of the cases, robotic arms are used in the scenario where the situations are fixed, situations are repetitive. So in that scenario, obviously, less computation is done through obviously classic approaches. But if we have such a general case, then selecting which planner would be a great thing. Coming to the part of sim to real gap, can you share some experiences on this? Because it's quite interesting.
I don't have a ton of experience from like my research and PhD. I do have some experience, and then just knowledge from reading other papers. So one thing which is nice to see is that inside of the MuJoCo simulation, like I've run the admittance control in there to do a grasping task of this sort of complex structure designed for like a space robotics, and tune the parameters inside of the MuJoCo simulation and ran it on the same robot, and the exact same controller worked on the real robot. So for, a little bit of a simpler task like that, you can actually port it and get a successful result. So that's really encouraging. I saw some result recently, which was really interesting. People showed a correlation between success of learned models in simulation versus success in real life. So one of the problems with sim to real is that if you train something like reinforcement learning, or if you try to optimize the model, which is bad, you're sort of optimizing for a case which is not realistic, and it can cause catastrophic failures when you actually deploy the robot in the real world. But this is sort of looking at it from a different perspective, where you say like, okay, well, if you just do it, end-to-end learning model, you can evaluate it in the sim, and there's a strong correlation between success in the sim versus success in real life. So you could train different variations of your policies, and then do some validation before you actually deploy it on a real robot. So that I think that's an encouraging result, sort of to overcome the sim to real issue.
You mentioned this picnic is moving toward MuJoCo. What are the differences and pros of MuJoCo that you find from Gazebo to MuJoCo?
I think the pros, I feel like it has better contact physics. So when the robot's trying to, pick up some sort of complex object and move it around, I think it has better results than Gazebo. I personally feel like it's easier to configure. Inside of MuJoCo, there's something called an MJCF file where you describe the kinematic structure of your robot, you describe the dynamic parameters, friction, and all of these things. And like the entire simulation description is all in one place, right? So if you sort of want to make a change, you just change it there. And they also have this viewer, which is a standalone application that you can just run. And you also run this like via Python if you want to. So it's very easy to install, very easy to run. And you can sort of like, you can take your MJCF file, your model description, drag it into the viewer, and then you can move the joints around and sort of do some sort of tests like, oh, I set my gains too low or too high because the robot's overshooting, right? So you can quickly iterate and wind up getting a model which is, more accurate to the robot. So I think it's easy to use, it's easy to install, it has pretty good physics. One of the disadvantages is that inside of MuJoCo, the model is fixed. So if I say like, oh, I have a robot in a scene and there's 3 blocks, I can make the robot do something with that, but I can't like spawn more blocks in, right? It's not like a video game engine, right? Where it's like you sort of spawn objects in on top of each other. Like inside of MuJoCo, it's a fixed model. And I think that's one of the reasons they can probably get faster and, more accurate simulation.
You cannot spawn multiple robots in it? That's what you're saying?
You can't dynamically do it, right? So you can have multiple robots, but it's all ultimately going to be in one file. Or inside of these files, you can include other files. But once the sim starts, yeah, it's just there. So you could try something like, okay, I'll have 10 objects and like they'll kind of be off the screen. And when I want them, I'll sort of pull them in. But it's not as nice as being able to sort of arbitrarily add and delete objects.
Okay. A lot of knowledge from Paul and a lot of discussion. It was really insightful for me. Got introduced to a lot of new things. Thank you for your time, Paul. And is there anything that you want to add that is left?
Yeah, I would like to say thank you for inviting me on your podcast. I'm honored that you reached out to me. So this was great. Yeah, I'm glad you reached out. Maybe just one final thing, just on people getting started in robotics. Just a few pieces of advice. I would say if you don't have a formal education in robotics, there's a lot of resources out there. I think there's a really good course on modern robotics by Kevin Lynch. You can get all the lectures for free on YouTube. I would put some effort in. I would learn at least a little bit of robotics formally, because I think what winds up happening is, we feel like we know these things, but until you sort of sit down and study it, there's always a little bit of confusion. Even just matrix transformations and what frame something's in, how to do these transformations. He goes over it in this course. So I recommend that. There's probably other courses as well. Yeah, that's one thing I would say. And then number 2, if you haven't already, I would build some sort of project, hobby robot or something. Because when you see it move for the first time and do what you tell it to, I think it does sort of create this spark of creativity and curiosity. And, it's going to make you want to do robotics a bit more. My first sort of hobby robot was 2 Revolute joints on a planar joint and a marker attached to the end effector. And I had it go and write my name. So, it's a very cool experience to see it once it finally writes it correctly.
That's a nice project, by the way. I was talking to Sebastian Castro as well. He also mentioned the same thing, that do some project. And when I asked him if someone has created a project of going from one point to another, then he started to bring in some technical stuff, that if he has done this, then what planning algorithm and what this and this. But the main thing is you have to do a project. Otherwise, how can someone judge whether you are running someone else's code, running a node, running a launch file of ROS or move it system, how someone is going to, because people have to get people to work with them. So if a person is not deep enough, it is going to affect the culture of the company as well. It's an honor for me as well to have you here, and thank you for also introducing me to the title of robotics scientist. This is the first time I have heard about it, and it's great. And keep doing the great work that you are doing, and also contributing to the open source software that you are doing. Thank you.
Yeah, thank you. Bye-bye.